Hey there, this is the final exam screencast question number 6. My name's Kevin Reynolds and we're going to get right on into it. So as is routine, we're going to go over a brief overview. With this question we're going to be looking at Lipinski's rule of 5, which is going to move us kind of into the concept of log P, what it is, how we calculate it, those types of different things. And then we're going to look at octanol and how that actually is affecting log P and why it's actually beneficial to use. So first things first, as a jumping off point, we're going to go into what Lipinski's rule of 5 is. Now, it's oftentimes used in drug development, drug design, and making sure that the drug is actually doing what it's supposed to do and it actually fits guidelines that are going to be supportive of what is meant of it. So his outline and his rules currently are: the molecular weight of the drug should be less than 500, the log P should be less than 5, H-bond donors, so things like alcohols and different nitrogens with hydrogens on them, things like that are going to be donors. You want those less than 5. Then H-bond acceptors, so things like normalized oxygen, not alcohols, nitrogens that just have a lone pair of electrons, those are going to be our acceptors. We want less than 10 of those. And then rotatable bonds. Now these are bonds that if you were to grab one part of it and spin or rotate the other side of it, you would get a difference or a change in a chiral center or things of that nature, or the actual structure would look different. So to dive into that right away, we're going to look at this drug itself, which is propranolol. So we're going to highlight a couple of different things. First, we're going to start off with molecular weight. Easy enough, simple enough, just add it all up and we get roughly 259. Now we're going to jump over and look at the donors first. The reason we're going to look at these first is the log P is a little more complicated. We're going to get into that and drive right into the log P. So when we're looking at donors, as mentioned, we're going to look at things kind of similar to these two structures right here, which is going to be indicating that we actually only have 2 donors. Next, we want to look at acceptors. Now, we know that this oxygen, and this nitrogen all are going to have lone pairs associated with them. So all of them actually get to be associated with hydrogen bond acceptors, which give us 3 hydrogen bond acceptors overall. Now, as I mentioned, we're going to look at rotatable bonds next. So you have to look at things that if you were to grab hold of it, if you were to grab hold of this bond right here and nullify this area and rotate this side, we would see a difference in the actual structure. So now we can note that we have 1, 2, 3, 4, 5, and 6 of these different structures. So what that's actually going to get us in indicating is that we have 6 of these. Now, without going into too much detail, we're going to mark out the log P. Now, the log P of this is associated to roughly 3. Now, we know going back that we need to be less than 500. Okay. Less than 5 for the donors. Correct. Less than 10 for acceptors. Good. Rotatable bonds less than 10. Yep. And log P less than 5. So we associated all of those and have all those. Now, let's look at log P a little bit more. So looking at log P a little bit more, it looks something like this. How you actually calculate that is what's the concept of our partition coefficient, which is going to be our concentration of octanol over our concentration of water. So this is looking kind of in a sense at a concentration of a organic solvent type thing and a non-organic solvent type thing. So what we want to do is kind of looking at this structure on the bottom, or this little design, is how much of it is going to be concentrated into the organic side or the octanol side, and how much is going to be concentrated into the water side. Now, kind of looking at why octanol is such a benefit to the system. Octanol is, in a sense, a solvent that is ultimately amphipathic. It's usually easily measurable, and it kind of relates into the concept of LFERs, or what are we going to look at with biological properties.